Hello everyone, my name is Dovaria Niketan and previously in this video lecture series we were discussing chapter number 2 AC circuits. Up to now we have discussed generation of alternating voltage, various terms related to alternating waveforms. Now in this video lecture we are going to discuss phasor representation of an alternating quantity. Let's start the phasor representation of an alternating quantity. Now we know that up to now we had studied various type of parameter in which we had studied two types of parameter up to now. First one is known as a scalar and next one is known as a vector. So I think all of you have an idea what is scalar and vector quantity. Scalar quantity which can be defined by with only magnitude. As an example, you can consider weight in kilogram or you can consider temperature. So to define weight or temperature, you just need one figure, its magnitude. But there are another parameters like velocity in a particular direction or force in a particular direction. So to define those parameters, you need their magnitude as well as their polarities, means their direction. So parameter, to define those parameters, we need magnitude as well as the direction of those parameters that are known as the vector quantities. Now here we have alternating quantity and we know that magnitude as well as the polarity of this alternating quantities is changing with reference to time. That means here we don't have a constant magnitude as well as a constant direction. So we cannot define alternating quantity in form of a scalar quantity or maybe vector quantity. That's why we need another method and that is phasor representation. So let's start how to represent alternating quantity in form of phasor quantity or in other way. What is phasor quantity exactly? For that, let's consider x-axis over here where we will going to mention theta means angle of a quantity over here. On y-axis we are going to define one current over here as we will consider sinusoidal current. That's why here throughout the chapter we are going to consider voltage or current in form of a sinusoidal manner. So here in this diagram we have a sinusoidal current over here. In this given circle we are considering a vector over here on positive x-axis means at 0 angle over here, and we are considering its magnitude as a amplitude of this sinusoidal waveform which is given in this figure over here. Now amplitude means, let me remind you that is the maximum value of this given function. So basically we had considered magnitude of this given vector as a maximum value of this given waveform, and we arrange that vector initially on 0 angle means this OA vector that is having magnitude of this maximum value of this waveform, and currently it is at 0 angle. And at 0 angle, if we find out its projection on y-axis, means basically we are finding out its magnitude or y component basically, means y projection. So as it is on x-axis, so its y projection is going to be 0. So here at 0 angle, projection of this vector is 0. That's why if we note down the point over here in this xy plot, so here we have a 0 angle and 0 value of the projection. That's why at the 0 angle means it's A point. We have a value of that projection is 0, so that's why point over here is on 0. Now let's suppose that we are rotating this vector OA in anti-clockwise direction. So after rotation of some angle, let's say theta. Now this vector is on this position that can be defined by this OB, and at this position angle theta we are defining the projection of this OB on y-axis. So if we define the projection of this OB on this y-axis, that will provide at theta angle. So here on this x-axis theta is going to be at this point at point B, and magnitude of that y projection is over here. So again we note down this point on this angle which is on point B. Now let's say again if we are rotating this point, we are rotating this vector, and now this is defining over this. Now again we are rotating this vector, and now let's suppose that this vector is on 90 degree. Now that is represented by this OC vector. And now if again we find out its projection on y-axis, so that will provide a C point at 90 degree and it will provide a magnitude which is going to be maximum and which is mentioned over here or drawn over here. Now again if we rotate this vector and if we plot vector at certain angle, so that is given by this OD, and let's find out the projection again related to this D point. So according to whatever the angle which is representing this D point, so we had considered same angle over here on this D point, and according to that we are getting the magnitude of that vector or projection of that vector over here. So we had considered this dot again. Similar way you can consider rotation of 180 degrees, so that will provide this vector OE, and again on that point at 180 degree we get projection, and at that projection we are going to get value, and that is 0 over here. So at this 180 degree this is represented by this point E. We are getting the y-axis projection magnitude 0, so that is given by this point E. Similar way you can define projection on next angle, that is shown on this F point. Similar way next, that is given by G. Again similar way if we continue rotating on this 360 degree angle on this full circle, we are getting various magnitude of various projection at various angles, and that are representing these points which are nothing but an instantaneous value of this given sinusoidal function. So basically from this diagram we can say that how we form this sinusoidal waveform, that is nothing but a representation of this rotating vector. So basically in inverse manner we can say that this alternating waveform can be represented by this rotating waveform. This alternating quantity can be represented by this alternating waveform can be represented by this rotating vector, and that is nothing but a phasor. So what is phasor? That is nothing but a rotating vector. So basically phasor and vector are same thing, but just there is one difference. When we consider phasor, it is rotating vector with respect to time. So this is the how we can represent alternating waveform in form of a phasor. Now in our next topic, let's discuss the importance of vector representation. When we represent any alternating quantity, it's very hard to represent any alternating quantity in form of waveform, especially when there are lots of waveform. So it is easy to represent alternating quantity in form of a phasor, as well as when we are going to add or subtract or multiply or divide any alternating quantities. If we consider it in graphical form or in directly mathematical form, in sinusoidal form, then these calculations are very tedious. By looking at complexity of this calculation, when we calculate in form of phasor quantity, it is very easy compared to when we done it with mathematical form or with graphical form. The method which represents the alternating quantity in easier way is known as a vector representation or phasor representation of an alternating quantity. There are some limitations of phasor representation. Let's go through it. Now, as we know that when we define alternating quantity, when we are going to calculate some examples based on this chapter, when we will consider any alternating voltage or alternating current, every time we are going to consider its RMS value. But here, as in our previous slide, we had seen that when we define vector, we consider its maximum value. So basically phasor diagram was formed based on the maximum value of an alternating quantity. But in practical life, when we consider the magnitude of any alternating quantity, we consider its RMS value. So always remember this thing. Let's suppose whenever you are going to calculate some examples, then at that time value of whatever voltage or current, whatever will be given to you, that will be always RMS value. And that's why we will always plot phasor diagram based on the RMS value, not maximum value. And that's why if you want to calculate the instantaneous value on various angle based on that RMS value, then you have to add one more step, because if you have a directly maximum value, then on certain angle you can directly derive the instantaneous value. But if you are given RMS value, first of all you have to convert it into maximum value, then you will be able to derive its instantaneous value. So this is one of the major limitation of the phasor representation. Now vector is assumed to be rotated. That means if a vector or in quantity, if it is in steady state position on a particular position, so it is easy to represent. But as we had considered, this vector is a rotating, that's why it is not possible to represent vector on all position on a paper. That's why it is difficult to consider. And last one, when we have two different alternating quantity with different frequency, it cannot be represented on same phasor diagram. So it is compulsory to have same frequency when you want to plot phasor diagram of various alternating quantity. So these are the limitations of phasor representation. Now based on that, when we will have a two phasor or alternating quantities, as we had discussed this term before, and that is phase difference. And when we are going to define phase difference. So first of all, what is phase difference over here? The phase difference or phase angle difference of an alternating quantity may be defined as the angle of lead or lag or with respect to a reference point. So that is phase difference. That can be defined in another way. The phase difference may be defined as the difference between phases of two alternating quantity or the angle difference between the two vector representation. So you can define phase angle difference by waveforms or by phasor diagram. Now let's discuss it. Here we want to define the phase difference, and for that we are considering two waveforms. In first waveform, here we have one diagram over here in which we had considered one waveform. Now let's consider another waveform. And if you observe these two waveforms, first one is of E1 and second one is of E2. Now if you observe that E1 is starting from 0 angle, in similar way E2 is again starting from 0 angle. So basically both are having same phase, both are having same phase angle. So there is no phase difference, and that is known as a zero phase difference, or in other way you can say that these both functions are in phase quantity, in same phase. Now let's consider another example in which again we will consider two waveforms of E1 and E2. But now if we observe this diagram over here, in this diagram E1 is starting from 0 angle, and if we consider E2, that is starting after some angle, and that is defined by phi. So basically positive cycle of E1 is starting from 0. That's why when we will define the phase angle of E1, we will say that it's 0. And when we will define the phase angle of this E2, we will say that it is phi. So now both are having different phase angle, and if you find out that difference, and that is going to phi minus 0 means phi. So this phi angle is a phase difference between these two quantities. And again if we define this specifically with reference to E1, E2 is starting after some angle or after some time. That means we can say that E2 is at lagging condition, E2 is after E1, and that is known as a lagging condition. So basically this phi degree with compared to this E1, that is lagging phi degree. In other way, you can also say in the reverse manner, with compared to E2, E1 is starting before. That means with compared to E2, E1 is leading with phi degree. So this was all for today's lecture. In next lecture, we are going to again continue this topic. So thank you for watching this video. Stay tuned with me.